Hi, Assalamualaikum warahmatullah. Good evening. Is everyone okay? How did you fare after listening to my fourth lecture, the hybridization and shapes of molecule? Are you okay? Hope you're okay because today we are going to cover more on hybridization, more like strengthening or enhancement of what you understand already, and some additional content in this lecture where you are going to see how the sigma and pi bonds are formed through the overlap of orbitals. Yeah, and all the materials that I'm going to be covering today is in the additional notes that I took from the textbook, chemistry textbook by Stephen Zumdahl. So just as a revision, because we did cover in the previous lecture how we can describe the bonding of ammonia molecule using the localized electron model. So localized electron model include obviously the Lewis structure, the valence shell electron pair repulsion, and now to include the hybridization. So first of all, for you to approach this type of question using the localized electron model is to complete the description by bonding in 3 steps. First write the Lewis structure. I hope this is not going to be a problem anymore. Lewis structure should be very well implemented skill for you now. And determine the arrangement of electron pairs using the VSEPR model. So first Lewis structure and then VSEPR. And the third is to determine the hybrid atomic orbital needed to describe the bonding in the molecule. So we'll go through the 3 steps. Yeah. For the Lewis structure for ammonia, I hope you guys are not getting anything else apart from this, where you have 3 NH bonding pairs and 1 lone pair of electrons on nitrogen. So the 4 electron pairs around the nitrogen atom require a tetrahedral arrangement to minimize repulsion. And we have seen that tetrahedral set is what? What kind of hybridization is tetrahedral? Sp3, yeah, Sp3 hybrid orbital obtained through combining 2s and 2p orbitals. No, the 2s orbital and 2p orbitals. So in ammonia, 3 of the Sp3 orbitals are used to form bond with 3 hydrogen atoms, as I described earlier and in the previous lecture. And the 4th Sp3 orbital is used to hold the lone pair of electrons as shown in figure 9.7. So that is figure 9.7. So one Sp3 to bond with hydrogen, the second Sp3 orbital to bond with another hydrogen, the third Sp3 to bond with another hydrogen, and the fourth Sp3 orbital is to be occupied by the lone pair of electrons. So that should not be any problem at all. Yeah, for you? So next, I'm going to very quickly go into your Sp2, which this shouldn't be a problem to you to understand because I have covered this before. So Sp2 hybridization, an example is ethylene or ethene. If you draw the Lewis structure of ethene, you're going to find that between the carbon and carbon, there is 2 pairs of bonding electrons making a double bond, and 1 pair here with hydrogen, another pair, and another pair. 4 CH bonds there. We also have learned that this double bond doesn't count as 2 bonds, it counts as 1 bond. Yeah. The double bond acts as 1 effective pair, so the ethene molecule is surrounded by 3 effective pair, and 3 effective pairs give you trigonal planar, trigonal planar with the hybridization of 3, yeah, 3, Sp3, yeah, 1s and 2p's. So you have Sp3 hybridization for that. So how is the hybridization achieved? By this s orbital mixing with this p orbital and that p orbital. So you have like this. It makes a trigonal planar shape with a bond angle of 120. This I covered previously, so it shouldn't be a foreign concept for you. Now, a double bond acts as one effective electron pair. Since the sp3 orbitals that we talked about for ammonia and for methane has an angle of 109.5, but the sp2 has an angle of 120 degrees because the 360 degrees in one round is divided into 3 bonds equally. So we have 120 degrees angle for each one. So a set of 3 orbitals arranged at 120 degrees angle in the same plane can be obtained by combining one s orbital and 2p orbital is as shown in figure 9.8. So that's 9.8. Yeah. That this is not something new. What is new? You can read all this. I have given you the notes. You can read it up. Make your own notes. Be very very aware that while you are doing any of your own reading or listening to my lecture, you must make your own notes. If you don't make your own notes, then you'll have a problem recalling what you listen or what you see. You have to engage the other senses, is your touch senses, your writing, your thinking process have to be engaged while you are learning. Otherwise, it will be a very, very quick thing to forget. Yeah. So you have also seen previously how Sp2 hybridization occurs in terms of energy level diagram. I have explained this previously. I will not repeat. You just have a look and I hope you immediately can understand what that is all about. What I want to focus on in this lecture is actually how the sigma bond and the pi bond, how they are formed. Now, between the carbon and another carbon, you see there is a double bond. Do you agree? Yes, there is a double bond between carbon of ethene. And the double bond consists of one sigma bond and one pi bond. So how do you describe the formation of the 2 bonds that exist between the 2 carbon atoms in ethene? So the first one is the formation of sigma bond. Ethylene actually is an old name for ethene. Yeah, it is an old name for ethene, is ethylene. So first of all, you must describe the formation of the sigma bond. Now, you must, I don't know whether you have learned this before, but sigma bond occurs or formed through the head-to-head collision when one orbital is mixed with another orbital or overlap with another orbital where the heads collide or where the heads mix, so they form sigma bond. Whereas pi bond is when the overlapping orbitals here meet side to side. Here, side to side. So you have pi bond is formed when you get side to side overlap, whereas sigma bond is formed when you get head to head overlap. Now let's have a look at the diagram 9.11 where you see the head-to-head overlap of one sp3 hybrid orbital and no, not sp3, this is sp2 hybrid orbital with another sp2 hybrid orbital that allows one pair of electrons to be shared between the two carbon. So there is the sigma bond formation in ethene. Note that each bond for each bond, the shared electron pair occupies the region between the atoms, between the carbon atoms. So this is the electron that is occupying that overlap of orbitals. So that is the formation of a sigma bond when two sp2 hybrid orbitals overlap head to head. Head to head. Now looking at the next diagram, which is figure 9.12, this is showing how the second bond is formed. The second bond is formed through the overlap of the p orbital. Do you remember? That the p orbitals in the carbon here? Here, this is the non-unhybridized. Yeah. Do you recall? Here there is the unhybridized p orbital, this one here. Now it stands erect, or it stands on the vertical, on the z-axis. So one carbon has that. Yep, this is the dumbbell shape of the p orbital on one carbon. This is another dumbbell shape of the p orbital on the other carbon. So when these two carbons approach one another, the p orbitals will overlap side to side. Yeah, side to side. So side to side overlap will make a pi bond. A pi bond. Now going back to this 9.11 diagram, there are three sp2 orbitals in one carbon. One is to overlap with the sp2 orbital of one carbon. Two more will overlap with hydrogen. One here and one here, making a carbon-hydrogen bond, and the second carbon, it has the sp2 overlap also with the s orbital of the hydrogen, and another sp2 overlapping with the s orbital of the hydrogen. So these are all the sigma bonds. So you have 1 sigma bond, 2, 3, 4, and 5 sigma bonds, and the pi bond, which is the sixth bond, is shown in figure 9.12. So are you okay with that? I hope this concept will become much clearer to you as we go along. Now, in the sigma bond, the shared electrons occupy the space directly between the atoms. Yeah. This shared electron occupy the space directly between the atoms, whereas the pi bond is formed from the unhybridized p orbitals on the two carbon atoms. In the pi bond, the shared electron pair occupies the space above and below the line joining the atoms. 1, 2. So these two, one cloud at the top and one cloud at the bottom, make one pi bond. Yeah, so that is how a pi bond is formed in ethene. I hope that's fine for you. There's no problem. Note that the sigma bonds are formed from orbitals whose lobes point towards each other, but pi bonds result from parallel orbital. Yeah, lobes pointing towards each other, meaning head-to-head overlap. Parallel orbitals mean side-to-side overlap. So a double bond will always consist of one sigma bond and another one pi bond. The shared pair will occupy the space for the pi bond above and below the sigma bond. Figure 9.13. What is figure 9.13? What is figure 9? Oh, there it is, figure 9.13. Yep. The carbon atom uses sp2 hybrid orbitals to form the sigma bond. This is repeating, and the example is shown here. So that is the complete picture of the bonding of ethene, the bonding that you will find in ethene. This is the combination of 9.12 and 9.11. So you have 9.13 like this. The orbitals used to form the bonds in ethylene or in ethene, and this is the Lewis structure of ethene. So the green and red makes this one, 1, 2, 3, and 4. The green and green makes one of these bonds, and the blue and blue makes another one bond. Is that clear? Yeah, so this is something that is new, that is not in my lecture 4, not in my lecture 4. This is new. Next, I'm going to go into Sp hybridization. Excuse me. Now, Sp hybridization, as you can see, as you already being taught in the last lecture, Sp hybridization is for linear molecule. Now, linear molecule, this is, for example, carbon dioxide. So if you draw the Lewis diagram of carbon dioxide, you're going to find that it looks like this. You have double bonds, CO on the right side, and another double bond CO on the left side. So you have 2 CO double bonds, and each one of the oxygen has 2 lone pairs of electrons. Now, in CO2 molecule, the carbon atom has 2 effective pairs that will be arranged at an angle of 180 degrees. Remember VSEPR, when you have two pairs of electrons, when you have 2 bonds, when you have 2 CO bonds like this, you get a linear arrangement where the bonds will repel one another, so they become furthest apart from one another. And this is the furthest apart they can go. This is 180 degrees. This requires a new type of hybridization, which is Sp hybridization, involving one s orbital and one p orbital. This is not new to you. I have taught you this before. Please read up about these notes. I'm not going to read it for you here because the notes are with you. Internalize what it says, and then I'm just going to go straight into how 1s and p orbital hybridize to make this small lobe and big lobe for Sp, another small lobe and big lobe for the second Sp. When the two combines, you get a linear situation like this. So if you have the story like the CO2, you have carbon to oxygen, the Sp orbital and the Sp orbital on the carbon will overlap with Sp3. Now, how do we know that oxygen here is Sp3 hybridized? Now, go back here. Go back to this drawing. If you make oxygen the center of your discussion, you have 1 bonding and 2 lone pair. So when you have 1 plus 2, 3 situation like this, you have Sp2. Yeah, Sp2. So oxygen is Sp2 hybridized like this with a bond angle of 120. So one of the Sp2 hybrid orbital will overlap with the Sp hybrid orbital of carbon to make a single bond here. Another one similarly happening on the right side of the molecule. And this green lobe will be occupied by a lone pair of electrons. This another green lobe, also a lone pair of electrons, similarly with these two. So you have the 4 lone pairs of electrons occupying the Sp2 hybrid orbital on oxygen. So in terms of energy level diagram, this is how Sp is achieved. You have Sp, Sp, and two p orbitals not involved in hybridization. So the p orbitals is 2py and 2pz will not be involved in bonding, will not be involved in hybridization rather, not bonding. It will not be involved in hybridization. You just get Sp. So how will that be used if you have a double bond or a triple bond? So I'm jumping ahead of myself here. I'm just going to still stick to carbon dioxide here. Yep, carbon dioxide. You have carbon, Sp hybridized, and then the two unhybridized p orbital, the one that I said here. Yep, these two unhybridized, there they are. And this is the Sp3 with the PZ unhybridized. I hope you are following this. Now, a more rigorous theoretical model of CO2 indicates that each one of the oxygen atom uses two p orbitals simultaneously to form pi bond to the carbon atom, thus leading to unusually strong CO bond. So, if this p orbital overlaps sideways with that p orbital, and this overlap, then you're going to have carbon Sp overlapping with oxygen Sp2 to make a sigma bond, and this Pz, yeah, top and bottom will overlap to make a pi bond. So that's why you get a CO double bond. Yeah, is that okay? Is that familiar? Yep, good. Now for another example, there it is. Excuse me. This shouldn't be here. Okay, this is what I was explaining to you earlier. This is your Sp on carbon, the yellow. The green are your Sp2 on oxygen. You have the overlap head to head, green and yellow to make a sigma bond. Overlap side to side between the blues. You have the Pz orbital of C, the Pz orbital of O make a pi bond on this side, and the Py orbital on carbon and the Py orbital on oxygen, the other side, will make another double bond on the left side of the molecule. So you have double bond happening here and double bond happening there. Now, when I say unhybridized is Px and Py, those are all arbitrary. This can be Px, this can be Py, this can be Pz, because they are degenerate. They are having the same energy level, having the same shape, only the orientation is different. So for the sake of discussion, this is a Py because it will overlap nicely with the Py of your carbon here. This is a Pz because it will overlap nicely with your Pz of the carbon here to make one pi bond on the right side and one pi bond on the right side. So you have carbon dioxide bonding formation in that way. So you have sigma bond, pi bond, pi bond. Yeah, is that clear? Okay, now after that, I'm going to give another example. The arrangement is a little bit funny here, but never mind. Another example is an ethylene or an ethene with a triple bond. Yeah, ethyne is when you have, that's it. When you have C triple bond in the middle and one hydrogen, it's also a linear. When you see linear, straight away your mind will say Sp hybridization. It cannot be any other hybridization. It will always be Sp hybridization if it is linear. So for Ethyne, in Malay, maybe some of you still recall the name Ethuna, yeah, Ethuna in Malay, but it's Ethyne in English. Now, because the triple bond counts as one effective repulsive unit, each carbon has two effective pairs. Yeah, in this you have each carbon, you have one pair here, one pair there. This carbon has one pair here, one pair there, so it will be linear, requires a linear arrangement. Thus, the carbon atom will be sp hybridized with two unchanged p orbitals. Refer to figure 9.16. Go back to 9.16. There you go. You have sp hybrid orbitals and two unhybridized orbitals there. Yep. One of the opposite orientation, see figure 9.14, sp orbital is used to form a bond to hydrogen atom, and so on and so forth. There's so much there. So if you look to see the, yeah, this is the Ethyne. Yeah, this is the Ethyne. So talking about Ethyne, just one second, let me adjust the page. Okay, adjusting the page a bit. Okay, the Ethyne here. Oh, this is not Ethyne, this is an nitrogen molecule. But never mind, it is the same as your, this is the, as your, maybe it's an, it is for you to make an exercise, how the Ethyne molecule, the bonds in Ethyne molecule are formed. So you can model your answer on this one and try to see how C2H2 or Ethyne, the bonds in it are formed. So that would be for you to practice. You can stop this video for a while now and you can practice drawing until you get the answer. So, okay, going into nitrogen. Nitrogen molecule. Yeah, the Lewis structure for nitrogen is like this. I hope you get a triple bond between the two nitrogens and a lone pair of electrons on each nitrogen. So you have a linear arrangement. Linear arrangement means sp hybrid orbital. So here you are, you have the, this is your sp hybrid orbital, this yellow and another yellow sp hybrid orbital. And then how do you get two pi bonds? Because these three bonds, one of them is sigma bond, two of them will be pi bonds. Yeah. So this is the overlap sideways of the unhybridized p orbitals on nitrogen. So you have the pz overlapping sideways with the pz of this nitrogen, making one pi bond. Py, one there, and then another py of nitrogen, making hybrid making sideways overlap to make pi bond, another pi bond. So these four dotted lines that you see here are representation of two pi bonds. So if you want to draw the whole picture of a nitrogen atom, you have the yellow sigma bond and you have the blue overlap to make two pi bonds. Yep, so that's how you get. So that is the coverage for Sp, Sp2, and Sp3. Now we go on to the next hybridization, which only can happen for atoms or central atoms that are located in the third shell of in the third row of the periodic table. That means it must have the d orbitals, because d orbitals only appear on the third shell. The first shell only has s orbital, the second shell has s and p, the third orbital has s, p, and d. So it can only happen to phosphorus, for example, because phosphorus is on the third row in your periodic table. Now, to illustrate the Dsp3 hybridization, we look at the molecule PCl5. Now, if you draw the Lewis structure of PCl5, it will look like this. Yep, expanded octet for phosphorus here, more than 8 electrons on phosphorus. It is possible, expanded octet is possible because it has d orbital. The phosphorus atom has d orbitals. Now, Dsp3 hybridization involves 1 d orbital, 1 s orbital, and 3 p orbitals, as shown in figure 9.21. There you are. This is 9.21. This is the Dsp2 hybrid, Dsp3 hybrid orbital of 5 equal lobes waiting to make a bond with oncoming atoms. Yeah. The Dsp3 hybridized phosphorus atom in PCl5 uses its 5 Dsp3 orbitals to share electrons with 5 chlorine atoms. Note that a set of 5 electron pairs around a given atom always requires a trigonal bipyramidal. Now, when you have 5 bonds surrounding a central atom, it will have to be trigonal bipyramidal. Trigonal bipyramidal has hybridization of Dsp3. Dsp3, 5. The Lewis structure shows that each chlorine is surrounded by 4 electron pairs. Have a look here. Yeah, 4 electron pairs, 3 lone pairs, and 1 bonding pair. Note that a set of 5 effective pairs around a given atom always requires a trigonal bipyramidal arrangement. So now we can describe the bonding in PCl5. The 5 PCl sigma bonds are formed by the sharing of electrons between the sp3 orbital of the phosphorus and the sp3 orbital on each chlorine. So the chlorine, if you look at chlorine here, chlorine has 1 bonding pair and 3 lone pairs. So 4 pairs is sp3. So chlorine has sp3 hybrid, phosphorus has Dsp3 hybrid. The overlap is like this, so you have nice overlap between 1 chlorine to phosphorus. Through that head-to-head make a sigma bond, another head-to-head make another sigma bond, third, fourth, and fifth sigma bond. The structure of PCl3 molecule is shown here, and the orbitals used to form bonds in PCl, not PCl3, PCl5. In PCl5 like this. So that is what you see in there. So I hope you will go through the notes slowly. You can pause this video if you need, so that you can practice or make your own notes. And there is an exercise here given for the Lewis structure of iodine 3 minus. So remember, for the minus, you have to have a square bracket. Remember, there must be a square bracket. If you do not put a square bracket and a negative charge there, then your answer will be wrong. Remember, when you have a quiz Friday, hopefully there will be a quiz, an online quiz. If you have a question, I'm not the one who is just going to set the question. It will be somebody else. So you might well be getting one question with a charge species. Remember, count the electron. If it is negatively charged, you count it as 1 electron. Add additional. If it is positively charged, you minus 1 electron. And when you draw the Lewis diagram, you must put the square bracket and the appropriate charge for a full mark. Remember, for a full mark. So if you look at this, for your iodine on the left side here, you have 1 bonding pair and 3 lone pairs. So that must be sp3 hybridized. Am I right or wrong? I'm right. Cannot be wrong. On the left-hand side here, you have one bonding pair and 3 lone pairs. So that is also Sp3 hybridized. And on the iodine in the middle, you have 2 bonding pairs and 3 lone pairs. So that will have to be Dsp3. Yeah? Dsp3. So, and you have to show that the central iodine has 5 pairs of electrons that requires Dsp3 hybrid orbital, and the central atom is Dsp3 hybridized. So you have the overlap. I hope there is a picture of the overlap here. Nope, there's no picture of the overlap, but that's fine. You can draw the overlap picture yourself. Yeah, try and practice the overlap. It's really very simple. And finally, you have D2sp3 hybridization. For example, for the molecule SF6, SF6 is the drawing is like this. You have 6 pairs of bonding electrons around sulfur. It is D2sp3. D2sp3. 6. I don't have enough fingers in one hand. So D2sp3. Yep, so 6 bonds. So you have D2sp3 hybridization, and the picture looks like this. It is an octahedral arrangement. It has to be octahedral arrangement for 6 bonds. So you have 4 on the equatorial position and then 2 in the axial position. Right? So that is really quite simple. And there's one question here. How is the xenon atom in XeF4 hybridized? How is the xenon atom in XeF4 hybridized? So you see, when you draw XeF4, this is what it looks like, the Lewis structure. You must start with the Lewis structure. So around xenon, you have 1, 2, 3, and 4 bonding pairs, 2 lone pairs. So it will have to be D2sp3. On the fluorine, you have 1 bonding pair and 3 lone pairs. So it is sp3. Similarly with this, sp3, sp3, sp3. So you have that kind of overlap. So xenon here will be overlapping with fluorine. The sp3 hybrid orbital of fluorine. This looks like s orbital, but it is not. It is sp3 because of the lone pair. Otherwise, this will not give you a good picture of the lone pair. But it is giving you a very accurate picture of the hybridization of xenon. So 4 bonding pairs and 2 lone pairs for your xenon. Yep. So as a summary, the localized electron model hybridization must involve 3 distinct steps. One is to draw the Lewis structure. Number 2 is to determine the arrangement of electron pairs using VSEPR model. And number 3 is specify the hybrid orbitals needed to accommodate the electron pairs. So it is important to do the steps in this order. For a model to be successful, it must follow nature's priorities. In the case of bonding, it is clear that the tendency for a molecule to minimize energy is more important than the maintenance of characteristic of atoms as they exist in the free state. Yeah, so on and so forth. Please read up about this, understand what this is all about. Yeah, and there are some practice exercises. The carbon monoxide BF4 minus XeF4. So I'm just very quickly going to go through carbon monoxide. This is very familiar to you. So carbon monoxide looks like this. You have the carbon overlapping with the oxygen here. Also sp hybridized. And the pi bond occurs through the overlap of the unhybridized oxygen, when you have Sp, you have Px and Py unhybridized. This is also has Px and Py unhybridized. So you have Py here overlapping with Py, making a pi bond, and this can be a Px, this can be a Pz, depending, overlapping with another one to make another pi bond. So you have double bonds, triple bond. Yep, there. One sigma bond, two pi bonds, you get a triple bond. So for Bf4 minus, this is the question. Bf4 minus is like this. So please go through this, how it is drawn. Remember, there must be the charge, the square, and then how the these are electrons, one pointing up, one pointing down. Electrons, when they are paired up, they always will have the opposite spin. So you cannot have two electrons having the same spin. One must go up, one must go down. That is how it is. So a pair of electrons cannot have the same spin. It is one of the rules when you pair up electrons. So you draw them like this, one with the head going up, one with the head going down. So that is Bf4 bonding, looking like that. Yep, that is how the sigma bonds are formed between boron and 4 fluorine atoms. Xenon F4, you have xenon F2. This is how the Lewis structure looks like. This is 2 bonding pairs and 3 lone pairs, like that. It looks like a linear, but it is not actually a linear. It is a trigonal bipyramidal with lone pairs being invisible. You cannot see these lone pairs, but they are actually trigonal bipyramidal. Yep, like that. These are all lone pairs. Those are bonding pairs. So in this table, figure 9.24, this is just another summary. If you have 2 number of effective pairs, you get a linear with Sp hybridization. That is how it looks like. 3, you get a trigonal planar. Sp2, that's what it looks like. 4, and so on. This, I have gone through this table with you in the previous lecture. So that's it. This will finish all your localized electron model that includes the Lewis structure, the VSEPR, and hybridization. I will be posting questions to you on the Telegram page, and I would like you all to try and answer that question just as a practice before you go into your quiz on Friday. So that's it, guys. Thank you very much for your attention. And I hope what I have covered with you here is easy to understand. Otherwise, you have a discussion among yourself. You can ask me if you want. But the notes are very clear. It's taken from the textbook by Zumdahl. It is a well-established textbook. Okay, that's it. That's all for now. I hope you have a lovely week ahead of you. This is just Monday, 4 more days. Have a good week and a productive one. Take care. Assalamualaikum and bye-bye.